In this video, we're continuing exercise 2114, but instead of starting with acid chlorides, in this video we're going to be starting with less reactive carboxylic acid derivatives. Remember that acid chlorides are the most reactive carboxylic acid derivative, followed by acid anhydrides, and then esters, and then at the very bottom, amides. Well, amides are what we're starting with here. We have a carbonyl, carbon double bonded to oxygen, with an amine on one side. That means we're dealing with an amide here, and that's not especially reactive. And then if you look at the nucleophile we're working with, it's barely nucleophilic at all. It has a positive charge. And so here, the mechanism is going to involve more proton transfers to change the reactivity and the stability of these molecules in order to get them to react. We're still going to have the same process in terms of nucleophilic acyl substitution, the same essential steps. After all, if you look at the molecules, you'll notice that a lot is in common with what you have in the reactant, a carbonyl with 4 carbons, and what you have in the product, a carbonyl with 4 carbons. The difference is that you have this NH2 here, and that it is replaced by an OH in the product. And so the NH2 is going to act as a leaving group. So we know we're going to have loss of a leaving group, and the nucleophile, which is ultimately going to come from this water, or hydronium, that's going to be the sort of nucleophile. So we know we'll have nucleophilic attack. Those two staple steps, the two perennial steps in any substitution reaction, nucleophilic attack and loss of a leaving group, will happen here. They'll just be bookended and sandwiched in between a whole bunch of proton transfers to change the reactivity of stuff. So let's see how that works. And first, let's take just a second to talk about why amides are so unreactive, relatively, compared to the other carboxylic acid derivatives. Well, of course, one reason is that this NH2 is not a very good leaving group, so it's not likely to pop off. You're going to have to do a proton transfer to turn that into a good leaving group. But even before that, if you just look at the structure of the molecule, this nitrogen has a lone pair. Right? In general, nitrogen forms 3 bonds and has a lone pair. Otherwise, it has a formal charge. So it has a lone pair here, and you'll notice that that lone pair is allylic to the pi bond. And so this is actually just one of the resonance structures that this molecule could exist in. So you could imagine having a sort of bracket where you warn everybody, hey, this structure isn't quite right. The true structure is the average of all the structures in these brackets. And you would draw a resonance error that tells you to take the average. And if you have an allylic lone pair, to get a resonance structure for that, you could draw the allylic lone pair going toward the pi bond, and the pi electrons going away from the lone pair. So that the structure we'd end up with would be this here. There's even one other resonance structure you could draw besides that. We won't worry about that. Right now, my issue here is not, the thing I want to bring up and point out here is not so much that there's resonance here, although that is significant because these amides are present. That's how amino acids connect. A protein is just a series of amides, and the fact that there's resonance here means that the bonds in the amide, these bonds are somewhere in between single and double, and so they're very rigid. They don't rotate. So that is significant. But what I want to mention here is why this carbonyl carbon is not especially electrophilic. Sure, it's bonded to an electronegative atoms 3 times, the oxygen twice and the nitrogen once. But notice that it shares a bond to those lone pair electrons on the nitrogen. So in other words, the nitrogen is donating electron density to that carbonyl carbon, and that stabilizes any positive charge that would build up there. So you might look at that at first, and you'd say, slightly positive charge here. It's bonded to oxygen twice and nitrogen once. So they're stealing its electron density away, which is true. But these lone pairs go toward that positive charge. That lone pair goes toward that positive charge to help to stabilize it. And that's why the carbonyl carbon in an amide is not as electrophilic as in an acid chloride, for example. That's one of the reasons. Now, You'll notice a similar thing happens in esters. So you have an oxygen, carbonyl, and then a sort of ether on one side. You have lone pairs on the oxygen there, and that lone pair is allylic, and so you get the same resonance that makes this less reactive too. So amides and esters are the less reactive structures, the less reactive carboxylic acid derivatives, because there's that resonance structure that is donating electron density to the carbonyl carbon to make it less electrophilic. Okay. What that means is if we treat it with something that's not a strong nucleophile, here we barely have a nucleophile at all, we have hydronium. If we treat it with something that's not a strong nucleophile, that is not going to attack. It will not attack the carbonyl carbon. It's just not a strong enough electrophile to induce the attack. And so instead what we need to do is turn it into a better electrophile, and we've seen how to do this. We did this in acetal formation, imine formation, and or I should say acetal formation. We didn't quite do it, we did it in a way for imine and amine formation, but very clearly we did it as the first step in acetal formation. We had the carbonyl oxygen, which is slightly negative, steal one of the slightly positive hydrogens on hydronium. The electrons snap back onto the oxygen there to stabilize the positive charge on that oxygen, and that turns what was a very mediocre, if not bad, electrophile into a much better electrophile. Because now the oxygen is not just pulling electrons away from the carbonyl carbon through its electronegativity, it's pulling them away using the positive charge that the oxygen has. That positive charge is pulling on the electrons in this bond also. And so the carbonyl carbon loses a lot of that charge, the electron density, and becomes slightly positive. So if you're going to summarize that pattern we just did there as in one of the 4 curved arrow patterns, this is proton transfer. We're transferring an H+, which is a proton, from one molecule to another, this H+ right here. And notice the effect of a proton transfer. This is going to be a recurring theme. You do a proton transfer to change the reactivity or stability of a molecule. This molecule is not reactive enough. We can do a proton transfer to make it more reactive, a better electrophile in this case. The other molecule that we're left with after that proton transfer is water. What was hydronium is now water. And water can function as a weak nucleophile. This weak nucleophile can now attack this awesome electrophile. Now, that carbon already has 4 bonds. If it's going to form a new bond, one of those bonds has to break. The weakest bond is the pi bond, so that those pi electrons go to the most electronegative place nearby, and that's the oxygen. They go there to help stabilize that positive charge. And if you're classifying these curved arrow patterns, you would classify this one as a nucleophilic attack. The first step that always happens in any substitution reaction. Well, the first step that will happen in these nucleophilic acyl substitution reactions. One of the perennial steps, the steps that always appear. There's always nucleophilic attack and loss of leaving group somewhere. So what you get after that step, after that nucleophilic attack, is this pi bond breaks, those electrons go onto the oxygen and take away that positive charge. Moreover, you form a bond to what was the carbonyl carbon, from that to the water. So one of those lone pairs gets that done. And so you have that. Now, we have some charge here. The oxygen has 3 bonds, and so a full positive charge. So that's unstable. And I strongly encourage you to include the charges, first because you have to. They're necessary. They're parts of the structure, so points will be taken off if you don't have that. But also they give you hints about future things that you need to do. Charges have to be stabilized. Charges are places where the molecule is reactive, so they sort of guide your eye in where things need to be done. So we have our famous tetrahedral intermediate here. The carbon in the carbonyl carbon that was sp2 hybridized and trigonal planar, or flat, is now sp3 hybridized and tetrahedral. So we have a tetrahedral intermediate. The carbon in between these two oxygens and nitrogen is very slightly positive. All three of those atoms, the oxygen, the nitrogen, and the other oxygen, are pulling electron density away from that. And so that is attracting the electrons in each of those three, on each of those three electronegative atoms. But there are a couple problems where we can't do the loss of the leaving group just yet. First, the group that we want on this molecule has not yet been stabilized. It has this full positive charge, and our mission right now is to turn that into a more stable molecule. Well, you can change the stability or the reactivity of things by doing proton transfers. This has a positive charge, so we want to remove an H+. In other words, we want to add a base. The base we can add here is water. That's already present in the hydronium mixture. And we can do a proton transfer to change the stability of things. Here we want to make this molecule more stable, so the slightly negative oxygen in water steals one of these slightly positive hydrogens. The electrons snap back onto the oxygen to help stabilize the positive charge there. And the molecules you're left with after this proton transfer step is first hydronium, so we've reformed that hydronium, and then next we have a more stable tetrahedral intermediate after that step. So we still have our tetrahedral intermediate. This carbon in the middle is still very electrophilic, but now we do not, well, although the incoming nucleophile has been stabilized, we don't have any good leaving groups. So all of these lone pairs are trying to snap back on and reform a bond there, but in order for them to do that, something has to leave, and there's no good leaving group on this molecule. Well, what we want to treat as our leaving group is this nitrogen here. It's not a good enough leaving group yet, so what we can do to turn that into a better leaving group, to change the stability of things, or the reactivity of things, is a proton transfer. The nitrogen is slightly negative, it has that lone pair, and we have this acid here with hydrogens that are slightly positive. The nitrogen can act as a base, attack one of those slightly positive hydrogens. The electrons in the bond holding it onto the hydronium would snap back onto the oxygen to help stabilize that positive charge there. And when you do that proton transfer, you turn this bad leaving group into a good leaving group. So now, that lone pair on the nitrogen turns into a bond to a hydrogen that has a full positive charge, and that's an awesome leaving group now. Moreover, we also created water in that step, the hydronium, after it loses the H+. Okay, well, now that we have a good leaving group, these oxygens, the oxygens and the OHs, have a slight negative charge. The carbon in between all of these is losing electron density to an oxygen, a nitrogen, and another oxygen, so it's very slightly positive. And the lone pairs here want to form a new bond to it, so they snap back down and they kick off the good leaving group. So if you're thinking of categorizing this in one of the four curved arrow patterns, that would be loss of a leaving group. So what we would form there, is this lone pair would turn into a pi bond. That oxygen now has 3 bonds, so it has a full positive charge. The amine will leave. When it takes the electrons with it from that bond, it stabilizes the positive charge, so now that's going to act as ammonia. And that's really our product. I'm just going to draw this in a way that's more indicative of, more reflective of the true molecular shape, which is trigonal trigonal planar, so I'll have the oxygen and the hydrogen there. So moving that there. Okay, well, we're almost done. The charges tell us what we have to do left. We have an unstable positive charge there. How do you change the stability or reactivity of a molecule? You do a proton transfer. So we have a positive charge here. To get rid of it, we can remove an H+. In other words, we can take a base. And how convenient. We have ammonia, which is a classic Bronsted-Lowry base. The slightly negative nitrogen there can attack this slightly positive hydrogen. The electrons can snap back onto the oxygen in the carbonyl, and we'd end up with that molecule and ammonium, which is NH4+. Now, the ammonium is not our real focus here. Our focus is this carboxylic acid that we made. And that was what we wanted to make we wanted to explain making at the very beginning of this mechanism. Now, this may seem slightly more complicated than the mechanisms we were drawing last time, where we had an acid chloride, where we started with an acid chloride. But let's compare and contrast this mechanism with the previous one. We still have nucleophilic attack and loss of a leaving group as our two staples for how to get this nucleophilic acyl substitution done. The only difference between this and the other mechanisms we did were all of these proton transfers. Look at how many there are. There's one at the very beginning. That makes our poor electrophile a better electrophile so that the nucleophile can attack. There's one after the nucleophilic attack. That's because our nucleophile was weak. It was neutral. So it gained a positive charge once it added onto the molecule. We had to do a proton transfer to change the stability of that molecule, make it more stable. Then we had a bad leaving group. It wasn't reactive enough, so we had to change the reactivity of it by doing a proton transfer, turn our bad leaving group into a better leaving group. Finally, we were able to do loss of a leaving group, and after that, the carbonyl oxygen still had a hydrogen on it, which made it positive, so we had to do a proton transfer to make that molecule more stable. So the mechanism is really the same as any nucleophilic acyl substitution. The key steps are nucleophilic attack and loss of a leaving group. The only difference is using these proton transfers to either make something more reactive that isn't reactive enough, or stabilizing something that you want to stay on a molecule. Okay. Now, let's look at that and sort of compare that with how, in this next exercise, how this reaction is going to happen. First, look at the similarities here. You'll notice that the molecule on the left has a carbonyl with 4 carbons. The molecule on the right has a carbonyl with 4 carbons. You have the methoxy group, so here we have an ester, and you'd recognize that as a carboxylic acid derivative, where the thing bonded to the carbonyl is a leaving group in disguise. And what we see on the end is this ONA, which is interesting, and that's coming from our nucleophile. So we're really going to do this nucleophilic acyl substitution. We're going to substitute the ONA for OMe, and that's happening on a carbonyl. In other words, it's happening to an acyl group. So nucleophilic acyl substitution. Now, these esters are more reactive than amides, for sure, but they are still not especially reactive. They're much less reactive than acid chlorides. However, we don't just have a mediocre electrophile here. I mean, it's true. The carbonyl carbon here is not especially electrophilic. It has a slightly positive charge, but it's not especially electrophilic because one of the lone pairs on the oxygen in the ester uses resonance to donate electron density toward that positive charge, as we discussed in the previous example. The difference here is that our nucleophile has a full negative charge. Notice that sodium is a metal. Metals have very low electronegativity, so they give their electrons away to whatever they're bonded to, and here that means the OH is completely negative. So you have an ionic bond. And your real nucleophile is not NaOH, it's OH-. So the difference between this exercise and the previous one is that in the previous example, while we didn't have a very reactive carboxylic acid derivative, we had an amide, we also had a very weak nucleophile. And so we had to do a proton transfer before the nucleophile attacked. But in this example, we have an awesome nucleophile, strong base and a strong nucleophile, hydroxide. And so even though this is just a mediocre electrophile, that's okay. The nucleophile can carry the weight of both of these. It's a strong enough nucleophile for it to attack the carbonyl carbon at the outset. The weakest bond breaks, that's the pi bond. The electrons go up onto the carbonyl oxygen, the most electronegative place nearby. And if you wanted to classify this reaction, it would be the first of the steps that always appear in nucleophilic substitution. That's nucleophilic attack. That nucleophile attacks, and it gives you the famous tetrahedral intermediate. So these molecules turn into this pi bond breaks, becomes a third lone pair on the oxygen, which now has a full negative charge. And one of the lone pairs on hydroxide forms a bond to this intermediate, to what was the carbonyl carbon. Okay, so this is our tetrahedral intermediate. The carbon in the carbonyl, which had a pi bond, was sp2 hybridized and therefore trigonal planar, flat, now has all single bonds, and so can use all of its p orbitals, can combine them with the s orbitals to become sp3 hybridized, and therefore tetrahedral. So we have our tetrahedral intermediate. This oxygen with the full negative charge is very unstable, and the carbon next to it is pretty slightly positive. It's bonded, after all, to 3 oxygens, all of them pulling electron density away from it, and so the lone pairs there want to snap back down and form a new bond to that slightly positive carbon. And the best leaving group leaves, that's this alkoxy group, this methoxy group in this example. And this actually happens as an equilibrium. So there are, you might say, well, why does this one leave? Why doesn't one at the OH leave? That leaves 2, but when that leaves, you just go back to this previous product. And so there's this constant equilibrium going on, and you have a mixture of all the different reactants, all these different molecules at any given time. But sometimes when the OH snaps back, it kicks the methoxy group off, and in that case, you have this molecule here. The oxygen now has a pi bond to what was the carbonyl carbon, and is again, and now you have a single bond to the OH. Also, off of that, you have a strong base, methoxy group. Remember that Me just stands for a methyl group, so CH3. Well, we're not quite done yet. We have a strong base and we have an acid, so we're going to do a proton transfer. One more thing, before we do the proton transfer, if you wanted to classify this step in their 4 curved arrow patterns, this would be loss of a leaving group. The other essential step in any substitution reaction. Okay, so we have one more step. It's going to be proton transfer because we have a base and an acid. So we're going to take an H+ and move it from one molecule to another. The base steals the slightly positive hydrogen, those electrons go back onto the oxygen, and you end up with what's called a carboxylate. That's a carboxylic acid that has lost its acidic hydrogen. And then you have methanol also. Okay, well, somewhere in the solution there's still that sodium, and so they're putting that here to stabilize this negative charge. That might happen if, for example, you dehydrated all the salt, or you distilled all the solvent away. The crystals you'd be left with would have the sodium sticking to the negative charge, the positive sodium sticking to the negative charge on the carboxylate. But that is the product that we have. That is the product they were asking us to explain. That's this one. And you'll notice you see the methanol there too. So overall, we did this nucleophilic acyl substitution with a carboxylic acid derivative that's not especially reactive, an ester. But the reason why we didn't have to do all of those proton transfers that we saw in the previous example was because our nucleophile was strong, had a full negative charge, and so it was able to attack even this mediocre carbonyl carbon in the ester. There's this one last kind of strange step where the base that was the leaving group steals the acidic hydrogen in the carboxylic acid. Okay, let's try just one more for this exercise. If we look at this molecule on the left, it has a carbonyl and just one carbon next to it, and in the product, that same thing is there. The difference is what else is attached to the carbonyl. In the reactants, it's an OH, and in the products, it's an methoxy group, an OMe. In other words, we're taking a carboxylic acid, we're reacting it with an alcohol, and we're getting an ester. And this is a famous reaction, because this reaction is how your body forms triglycerides, and it's also how fruits and plants form the smells of fruits and vegetables, or mostly fruits. So, and fragrances and like flowers. So this is called the Fissure Esterification reaction. So it has that special name because it has a special significance. But you'll see that it's really just another nucleophilic acyl substitution. So notice we're going to have our nucleophile, methanol. It has no charge here, so we know we're in for some proton transfers. And we also have some acid catalyst there. Okay. So how does this happen? Well, we'll start with our carboxylic acid. Notice that this is acetic acid. This is vinegar. And so you can take vinegar and treat it with methanol. Remember, the Me is just a methyl group, so this is really just this, where this right here is a CH3. So the methanol molecule can swoop in. Now, the problem with this is this carboxylic acid is not especially electrophilic. I mean, sure, it's slightly positive because the carbon there is losing electron density to both of the oxygens. One of them it's bonded to twice, so it definitely is an electrophile and a significant one. But unfortunately, depending on the perspective you have, one of the lone pairs on the oxygens here is allylic to that pi bond. And so it can go towards it through resonance and use that lone pair, and its negative charge can help to stabilize the positive charge on the carbonyl. And that's what makes this not as strong of an electrophile as you would think. Now, it would react with a strong nucleophile, no problem. It's definitely an electrophile. But we don't have a strong nucleophile, we have a very weak one. Our nucleophile has a slight negative charge on the oxygen, but it does not have a full negative charge. And so it's perfectly fine not reacting with anything. So we have to entice it to react by doing a proton transfer and making the electrophile as strong as we possibly could. Now, when you see these brackets with an acid catalyst, what that means is you have some strong acid added to the methanol. And so the methanol molecule in solution is not just regular old methanol. A strong acid will have stuck this H+ onto it. And that oxygen is bonded to 3 things, so it has a full positive charge. So that's what the methanol really looks like in this acid-catalyzed solution. And those brackets with the H+ inside of them mean acid-catalyzed reaction. We've added a strong acid to this cauldron. Okay, well, a similar thing happens here as happened above. To make this electrophile a better electrophile, the oxygen in the carbonyl, slightly negative oxygen, steals one of the slightly positive hydrogens in this conjugate acid of methanol. The electrons in the bond holding the hydrogen there snap back onto the oxygen to help stabilize the positive charge that's there. So if you were classifying this as in one of the 4 curved arrow patterns, you would notice that this is a proton transfer. And we're doing a proton transfer to change the reactivity of this molecule. This is not electrophilic enough, it's not reactive enough. With a proton transfer, we add some positive charge onto this molecule, and that makes it more reactive, a better electrophile. Okay, well, this is actually an equilibrium reaction, and what we'd get after this proton transfer is an oxygen with a hydrogen on it. That oxygen has 3 bonds and therefore a full positive charge. That full positive charge adds to the electronegativity of the oxygen and makes this carbonyl carbon really slightly positive. This positive charge pulls on the electron density in this bond even harder than it was pulling before. So now we have a much more reactive electrophile. And our methanol molecule, which is what we get after we do this proton transfer, that weak nucleophile, even that will attack. Now the oxygen is slightly negative, so it'll move in, swoop in, attack the carbonyl carbon. The weakest bond, the pi bond, breaks. The electrons go to the most electronegative place nearby. That's the oxygen. It goes there to stabilize the positive charge there. Now if you're trying to classify what happens here in one of the 4 curved arrow patterns, you'll notice this is nucleophilic attack, one of the essential steps in any substitution reaction. Okay, what you get after that step is this pi bond is no longer there. It is a lone pair on the oxygen, and that takes away the positive charge on that oxygen. This lone pair on the methanol now forms a bond to what was the carbonyl carbon. Oops. That oxygen now has 3 bonds and therefore a full positive charge. Okay, well, we have our famous tetrahedral intermediate. And let me draw this bond here closer to the middle so it doesn't look so strange. So we have our famous tetrahedral intermediate. The carbonyl carbon was sp2 hybridized and trigonal planar, therefore flat. Now it's sp3 hybridized and tetrahedral. Okay, well, the charge on this molecule gives us a hint at what we need to do. We need to stabilize that nucleophile so that it stays on the molecule. Now it'll pop off, technically. These are equilibria reactions. So it could just pop off, but it could also be stabilized. And if it's stabilized, then a new set of reactions can happen. So another methanol molecule can come along. The slightly negative oxygen in the methanol can steal one of the slightly positive hydrogens. The electrons snap onto the oxygen to help stabilize that. And you'll notice here we're changing the stability of a molecule by doing a proton transfer. So the molecule we have left over after this is a stable tetrahedral intermediate. This hydrogen will now be bonded to one of the loose methanol molecules in the solution. The electrons will snap back onto the oxygen to stabilize the positive charge, which won't be there anymore, and so we have this relatively stable molecule. Okay. So, at this point, we have the incoming nucleophile is stably on the molecule. The OH, which was our leaving group, though, needs to leave. And it's not a good leaving group right now. In other words, it's not reactive enough. Well, what can we do to change the reactivity of something, to turn a bad leaving group into a good leaving group? We can do a proton transfer. The proton transfers change the reactivity of things. So the slightly negative oxygen in this leaving group can attack one of the slightly positive hydrogens in that conjugate acid of methanol that we made. The electrons would snap back onto the oxygen to stabilize the positive charge there. And the overall effect would be that we have just a regular methanol molecule now, and our tetrahedral intermediate now has a full positive charge and so it's an awesome leaving group. Let me draw the bond to this other hydrogen there. You can see that if it leaves, it will just be water. So this is an awesome leaving group now. So now that we have a good leaving group, these oxygens are slightly negative. They feel the slightly positive charge on this carbon. That carbon is, after all, bonded to 1, 2, 3 oxygens, so it's losing a lot of electron density, and so those lone pairs snap back down and kick this awesome leaving group off. So if you're trying to classify that, this step would be loss of a leaving group. The other essential step in any substitution reaction. All right, well, after that step, what we have is the methoxy group still on there. Now we have a double bond to this oxygen, which still has a hydrogen on it, and so it has a full positive charge. And our leaving group left as water. All right, well, we're almost done. The positive charge on this oxygen gives us information about the last thing we need to do. This is not stable. We need to make this more stable. How do you change the stability of a molecule? You do a proton transfer. Here, this has a positive charge, so we want to remove an H+ in order to remove that positive charge. You remove an H+ by adding a base, and water here can act as that base. The slightly negative oxygen could steal one of those slightly positive hydrogens. The electrons would snap back onto the oxygen to help stabilize the negative charge there, and the product you would be left with after that proton transfer would be this ester. We'll also have hydronium, which you notice is the acid catalyst that we could have started with. Okay, so and this is the molecule that we wanted to explain getting. So if you look back at the original molecule, you'd see that's the ester. We have that methoxy group attached to the carbonyl carbon. That's the ester that you wanted to form. So here we have the staple steps of any substitution reaction. We have nucleophilic attack and loss of a leaving group. In between, those two steps are sandwiched in between a bunch of proton transfers that each change the stability or reactivity of a molecule. We had to do a proton transfer in the beginning in order to turn the carbonyl carbon into a stronger electrophile, because our nucleophile was really weak. So we did that proton transfer to increase the reactivity. Because the nucleophile had no full charge, after it reacted, it had a positive charge. It was neutral, and it lost some electrons to form this bond, so it had a positive charge. So we had to do another proton transfer to stabilize that molecule, to make it less reactive so that it would stay on the molecule. Next, we wanted our leaving group to leave, but it was a bad leaving group. It was not reactive enough. So we wanted to make it more reactive. You can change the reactivity of things by doing a proton transfer. We put an H+ on it to make it more reactive. Once we had that there, we did the loss of a leaving group. And after the leaving group left, we still had a positive charge on the molecule. Well, that's unstable. We want our final product to be stable. We don't want it to have a full charge. And so you do a proton transfer to stabilize that charge. Proton transfers change the reactivity or stability of a molecule. Overall, though, the essential steps are the nucleophilic attack and the loss of a leaving group. This particular mechanism, as I mentioned, is called Fissure Esterification. What it is creating an ester by combining a carboxylic acid and an alcohol. And it's significant because this mechanism is the exact mechanism for how triglycerides form in your body between glycerol and alcohol and fatty acids, which are carboxylic acids. And it's also how plants make fragrances in fruits and flowers.